Topic 3.3 Standard Test Methods and Interpretation. On creep test. Creep occurs when a metal is subject to a constant tensile load at an elevated temperature or high temperature. And if you have a look over here, it's a good example of the turbine engine having the metallic components experiencing high temperature and high pressure in service. As I introduced you over here is the diagram showing two sections of the turbine engine. The first is the cold section and the hot section. In action, the air intake will get through the fan over here and then get through the compression section. And after that, once it gets compressed, it's going to the combustion section before going out by the exhaust. So the fan blades at the front here might be subject to the temperature of about 200 to 300 Celsius. And then once it gets through the compression section, the temperature might go up to for about 5 to 600 Celsius. And for the compression section, the temperature might go up beyond 1000 Celsius. And can you imagine that the metallic parts used for these all three sections have to withstand its range of temperatures and all is subject to creep? Because metals undergo a time-dependent increase in length and is normally at the temperature higher than half of its melting point. And this is important that we have to evaluate the mechanical performance of the metals using this application. So the creep test measures the dimensional changes which occur when subject to high temperatures at constant loading. And to do the test, we can follow ASTM E139. You can find it online as well. Over here, you can see the creep test machine, which is quite similar to one that we can do the tensile test, but with the option of having the furnace over here to apply the temperature while doing the test. The test sample is gripped by both ends while applying the constant load in the longitudinal direction. And at the same time, we have to attach the thermocouple so that we can monitor the temperatures during the test. And before we starting the test, we have to grip on the extension gauge in order to measure the extension over the gauge length during the test. And once we starting the test by putting the sample at particular temperature, for example at 300 Celsius, the metal within the gauge length will experience a gradual change in length, and that will be recorded onto the software. And for summarize, the creep test will be carried out at the constant load and constant temperature, and then we'll give the parameters, the extension, and the time that we're doing the test. After the test, we can obtain the so-called creep curve as you can see from this picture. Along the x-axis is the time that we record, and along the y-axis is the strain that we can obtain by having the extension divided by the original gauge length. As we plot the strain that varied with time, we'll come up with the curve looking like this and can be divided in three different sections. So a typical creep curve shows three distinct stages with different creep rates. And if we're talking about the rate, it means you have the parameters divided by time. Now I'm going to talk in more detail on different stages of the creep behavior. First, on the primary creep, which provides decreasing creep rate. As you can see from this first section of the curve, this will go on a little while before we moving into the secondary creep in the middle here. The secondary creep will give the representing constant creep rate, as this portion of the curve is quite a linear portion. And to this, we can obtain the creep rate by taking the slope of the curve, which is d strain by dt. And it is the minimum creep rate because the slope is the lowest among the three regions. And it also represents the creep rate of the materials. Beyond this stage, the materials will proceed to the final stage of tertiary creep, and that will yield a rapid creep rate until failure. As you can see here, the curve rising very rapidly up to failure. So there are three stages of the creep behaviors: primary, secondary, and tertiary. And we use the secondary creep in order to monitor the service life of the metallic components. As the test data is the plot of strain against time, therefore we can evaluate approximate service life of the metals. And in service, we have to stop using that metallic component just before it arrives through the tertiary creep. And once stop using it, you replace it with the new one. So you're safe now not facing the situation that the metal component will fail under creep. And this is how we extract the information from the creep curve for our engineering design. And this slide shows the effect of two important parameters which are stress and temperature that affect creep properties of the metals. First, on the graph on left-hand side showing different creep curves tested at different stress levels. If you have a look on this first one, when we're doing the test at low stress, which is sigma 1, giving low creep rate as you can see from here, and once we increase the stress to sigma 2, the curve moves up. And then when we apply much higher stress levels, such as sigma 3 and sigma 4, sigma 5 and sigma 6, you can see that the slopes all increase. And that will give you increasing creep rates and the shorter life of the metal under creep in service. Therefore, the higher the applied stress, the greater the creep rate and the shorter life of the metals. Another parameter is temperature. Again, over here is the graph showing two different creep curves. One's tested at low temperature, and once we increasing the test temperature, we now obtain another one tested at high temperature. Again, you can see that the slope of the curve increases with increasing test temperature. And the higher the temperature in service, the greater the creep rate and the shorter the creep life of the metals. And therefore from here, two important parameters that are stress and temperature will give the similar trend to the creep rate. And let's now hear some solution to creep. I'm introducing you again the diagram of the turbine engine. And that is because the metallic parts involved into this turbine engine are subject to creep at different stress level and different temperature. So as an engineer, we have to select proper metal that can be used for particular engineering applications. And normally, high temperature alloys can withstand high temperature. And high temperature alloys are, for example, nickel-based superalloys, and that can be used at the combustion turbine blade. As you can see in the picture down here, there would be other type of superalloys as well, like cobalt-based superalloy or ferrous-based superalloys. And this is because normally that high melting point alloys will have high creep resistance or lower creep rate, and therefore can withstand the stress and temperature in service at longer life. And one more thing that I want you to keep in mind as an engineer is not just that you select the proper material for a proper engineering application. Like in this case, the design is also important, as I'm giving you the example here that the turbine structure is designed to have the canals or the airflow that help cooling down the whole structure very quickly, like one over here and along the cross section, and also along the side of the turbine blade. And you can see that how important it is for a proper selection of the material and also the design of the component itself.